You ever stop and think about light? I mean, really think about it. How can a simple beam of light create these crazy mind-bending illusions on a hot road, but also be the very thing that powers our entire internet? Well, today, we're going to dive right into the physics of light and uncover the secrets behind some of its strangest and most amazing behaviors. So let's start with something I bet you've seen. You're driving on a scorching hot day, you look ahead, and it looks like there's a shimmering puddle of water way up the road. But then, as you get closer, poof, it just vanishes. Gone. So what in the world is going on there? It's not magic, I promise you. It's pure physics. And to solve that little mystery, we first have to wrap our heads around the really fundamental idea. Light doesn't always travel in a perfectly straight line. You heard me. Sometimes it bends. Okay, so this bending has a name. It's called refraction. And you've definitely seen this before. It's the reason a straw in a glass of water looks like it's broken right at the surface. It happens because light actually changes its speed when it moves from one substance or medium, like air, into a different one, like water. Now this slide here shows the two golden rules of refraction. See this dashed line? We call that the normal. It's just an imaginary line that's perpendicular to the surface. So when light enters a denser medium, say from air into glass, it slows down and bends towards that normal line. But when it does the opposite, going from glass back into the less dense air, it speeds up and bends away from the normal. So how do we actually measure this light-bending density? Well, we use something called the refractive index, which we just represent with the letter N. All you need to know is this. A high refractive index means light travels much slower in that material, and it's going to bend a lot. A low index means light zips right through, closer to its top speed. Okay, this is where things get really cool. We know light bends away from the normal when it goes from a dense to a less dense medium. But what if we keep increasing the angle that it hits that boundary with? Well, it turns out you can actually trap the light so it can't get out at all. And this image shows that tipping point perfectly. Just watch as the angle of the light ray inside the water gets steeper. See how the escaping ray bends more and more away from the normal? Well, eventually, we hit this one specific angle. We call it the critical angle. And at that point, the light doesn't really escape. It's bent so much that it just skims right along the surface at a perfect 90-degree angle. It's the point of no return. So what happens if you push that angle just a little bit past that critical point? Something amazing happens. It's called total internal reflection, or TIR for short. And for it to happen, these two conditions have to be met. First, light has to be trying to leave a denser medium for a less dense one. And second, the angle it hits the boundary at has to be greater than that critical angle. We can see the whole story right here in this one diagram. The first ray of light gets out, it refracts. The second one hits that exact critical angle and just skims the surface. But look at that third ray. Its angle is now past the critical angle. It literally can't escape. Instead, it's perfectly reflected back down into the water, just like it hit a perfect mirror. That, my friends, is total internal reflection. Okay, so now we have all the pieces of the puzzle. We understand refraction, the critical angle, and total internal reflection. Let's head back to that disappearing puddle on the highway and finally figure out what's going on. And here it is, the big reveal. That shimmering water you see, it's actually an image of the sky. You see, the hot road heats up the air right above it. This makes that layer of air way less dense than the cooler air higher up. So light from the blue sky comes down, hits this hot layer at a really shallow angle, an angle greater than the critical angle, and gets totally internally reflected right up into your eyes. Your brain sees a reflection of the sky on the road and just assumes, hey, that must be water. The source material really hits the nail on the head here. It says the light bends to reveal things that aren't actually there. It is a perfect, naturally occurring optical illusion, and it's all powered by the physics we just talked about. And this whole idea of total internal reflection goes way beyond just highway mirages. I mean, this is seriously powerful stuff. It's the reason diamonds are cut with such specific angles. It's to trap light inside, making it bounce around internally a bunch of times before it shoots out as that brilliant sparkle. And it's the secret behind our entire global internet. Fiber optic cables use TIR to bounce laser pulses down these tiny glass threads for thousands of miles, carrying all our data at the speed of light. Now, trapping light is one amazing application of refraction, but we can also use it to control light's path with incredible precision.
And that's the whole job of lenses. You've got two main types. On the left, a convex lens, the kind that's thicker in the middle, bends light rays inward, making them converge at a single point. And on the right, a concave lens, thinner in the middle, does the exact opposite. It spreads the light rays out. And this bending isn't just random, it's completely predictable. Using what's called the lens formula, scientists and engineers can calculate exactly how to shape a piece of glass to form the perfect image. This little equation is the secret sauce behind designing everything from a simple pair of eyeglasses to the mind-bogglingly complex lenses in the James Webb Space Telescope. So really, when you take a step back, it's incredible. You see this amazing dual nature of refraction. On one hand, it's this wild force of nature that creates beautiful, sometimes tricky illusions like a highway mirage. But on the other hand, once we understand it, it becomes this incredibly powerful tool that lets us build devices that bring our entire world, from tiny microbes to distant galaxies, into sharp focus. So we've figured out what happens when light bends as a single ray. But light also behaves like a wave. So what happens when two of those waves run into each other and overlap? Well, that creates a totally different phenomenon called interference, and it unlocks a whole new world of shimmering colors and patterns. But that's a story for another time. Thanks for